about the parametric model and the idea of how we would model this decision boundary based on something where we've got some parameters. In the case of the Gaussian classifier, the parameters are a mean and a covariance matrix, or in the simplified case we ended up with of the linear classifier, we ended up with a weight matrix and a threshold, and we could build the threshold into the weight matrix to make that work. But this is going to lead us on to the general case of how do we estimate those parameters. And in order to estimate those parameters, we need to find a way of actually designing what is the mean that we should use and what is the covariance matrix that we should use. And the approach of supervised learning, and this is in contrast to what's called unsupervised learning, where we don't have any labels. In supervised learning, we design a pattern system using labels of things that we know. So suppose that we know that all of the examples over here are in class 1 and all the examples over here are in class 2. Those class labels are things that we are given. And these are things that we might have to have experts that label these things for us. So a classic example is loan decisions, for example, where we might want to have something in a bank that looks at various parameters and decides, do we offer somebody a loan, do we not offer somebody a loan? And those parameters might be added up, things like earnings, it might be some sort of credit history, it might be the amount of the loan that you're looking for. And it could easily be a linear classifier that's used to classify, to make that decision. And one way of building a classifier might be to take decisions that have been made by a person, by an expert beforehand, and look to replicate those decisions. So you train your machine based on the decisions that somebody else has already made. Now, there are dangers in this approach. If the decision is based on the opinion of a person, there's an idea that sometimes comes up around ground truth. So you don't have necessarily real ground truth about what would be a successful loan or not. All you have is a person's opinion about that ground truth. And although it's a little bit beyond this course, one of the interests and concerns at the moment is the ethical aspects of the types of decisions that you're making. If you're making a decision about whether or not to offer somebody a loan, that changes their ability to access funding that might allow them to do something. Maybe somebody needs a loan in order to buy a suit to go to a job interview. If they can't get that loan, then they're not able to get to the job interview, they might not get the job. So when you're building these types of systems, you need to be aware of where your expert knowledge is coming from. Another place that that labels have been expert systems or these learning systems have been suggested is in making decisions about job filtering. So you put in an application of something, you read it through for some words, and you put it in a shortlist or not shortlist pile automatically. Now, if you try and match the decision to a human, there might be what are called unconscious biases coming into your system. So it might be that the people who are doing the recruitment unconsciously make certain choices. So, for example, it's well known that if you send CVs into a human and ask them to shortlist or not shortlist, there are effects based on the surname of the person. So certain surnames, so in Britain, for example, some employers may well find that an Anglo-Saxon name like Smith might be easier for them to recognise. A name not from a European country might be more difficult for them to recognise. and there are significant results about these sorts of biases that can come up in assumptions that people make based on actually irrelevant information. And studies have been made on just you change the name in a CV and you get different statistics about whether you get shortlisted or not. So these are the sorts of things you need to be aware of. If you are using this type of learning system, be very aware about where those expert labels come from. But for now, let's assume that we have this expert knowledge or this ground truth, this truth of correctness, and we want to build a system that will learn to make the correct decisions based on this information. And this is called a training set, or a training data set. And the idea of the training set is that you have, let's call it a set X, so here I'm using uppercase X, and this is a set of pairs. So we have an input data point, a position, and a label, gamma I, so xi is the input, and the label is gamma I. And this is the true class provided by a supervisor or a teacher. Sometimes the words are used interchangeably. So supervised learning, you have this idea of a teacher that's telling you the answer. But there's a second thing that we want to do. So we talked about measuring what the error value would be for something. So once you've trained something, let's suppose we've done this successfully, you want to know how well it's done. But we don't have access to the true probabilities. We only have an estimate of the probabilities. And we just used all of this data to train our best classifying model. So actually what we need is some more labeled data, which we'll call a test set, which we can use to estimate how good this model is. And in practice, one of the questions that we have to decide is, if we've got a set of labeled data that we know, we have to decide how to split between the training and the test set so that we get a good estimate of how well we've done, but also we're able to build a good classifier out of this. And we can sort of think of it in this way. We've got a set of data that's available, and we have to decide how much do we use for training and how much do we use for testing. We could, for example, decide that we're going to use 50% for training, 50% for testing. That would give us quite a good estimate on the test set of how well we're doing, but actually what we'll find when you do the assignment is that if you reduce the amount of training data that you've got, the model that you're going to build is going to be less accurate. So there's a trade-off here. You want as much data as possible in the training set to be as accurate as we can get when we build our model. But if we use up more and more of it for the training set, we haven't got much left for the testing set. So we can't estimate how well we're going to do in the end. And so often we'll find that really the split ends up in practice being something more like 80-20 or even 90-10. So you'll have maybe 4/5 of your data for training, 1/5 for testing. It sort of depends how much you've got, really. If you get more advanced, and you want to test out the capability of a model, then you can use a rotation around different data sets. So you sort of train it and test it on different ways of chopping the data set up, and that will give you an idea of how well the data is doing. There are also some more advanced models that you can use based on reusing the test set, boosting type models and so on. We're not going to go into that here, but you might come across them in other areas. So one of the things that we need to do a bit of a recap on is just some information about how do we estimate the parameters in a Gaussian or normal distribution. How do we estimate the mean and variance? If you want more information about this, there's some supplementary info from the Webb and Copsey book, so you can look at that online, or we've got it on Surrey Learn, the supplement information bit about parameter estimation. And so the key thing here is that we're going to be estimating mean and variance. Mean is easy, variance, there are just a couple of things that you need to look out for. You might have done this a long time ago at school, so you might just want to remind yourself about how to do these, but I'm going to show a couple of examples from here. So these can sometimes get a bit confusing in terms of terminology, because we bandy about the idea of averages, but we also talk about means as being the mean of something, but we need to be really careful whether the mean that we're talking about is the true mean of the underlying distribution, or whether actually it's the average of the measurements that we've made. And if we have this average of the measurements, sometimes called the sample mean, so here we've got a sort of double use of mean here. If it's the sample mean, then that is the average of the number of samples that we've got. So it's just total number of samples in our test set or training set, sum over xi divided by n, divided by the number of samples. This is an obvious one. Everybody does this one. And this sample mean, we're calling x bar, or x bar of n in this case, this, if you've got some samples, that's just a number. You take them and you average them. But these things are samples from a random distribution. So suppose we pick 20 numbers, take their average, we'll get a value. If we take another 20 random numbers from our random distribution, we'll get another 20 numbers, we average them, we'll get another mean. And this mean is likely to be slightly different to the other one that we've got. So the slightly strange thing that happens here is that this sample mean that we've got is itself a random number. And it has its own probability distribution. And because of that, it has its own expected value, or it has its own mean. Now this takes it a bit of getting used to, because we've taken the sample mean here, and what we've said is that the sample mean follows a probability density, and that probability density itself has a mean. So the mean, which is this expected value, if we calculate it, it is actually the same as the mean of the underlying distribution that this came from. So this is sort of quite nice. This is useful. What it says is, if we choose 20 numbers from this probability distribution, average them, and then pick that number, take another 20 numbers, averaging and pick that number. If we carry on doing that, the average of this distribution that we get is the same as the original mean. So, yeah, question. Yeah, so let's take this probability distribution that we've got here, and we sample 20 different numbers from it at random. We take those 20 numbers, we add them up, divided by 20. That gives us our mean. And let's suppose the true mean was something like 1.5. But the average of the numbers that we end up with is 1.7. Let's take another 20. We average those. We get 1.4. We take another 20. We average those. We get 1.55. We carry on doing that, and we see a probability distribution. We see a sort of histogram clustered around the mean, but it's not exactly always equal to the mean. But the useful thing is that it clusters around this point mu, that it clusters around the true mean. So the next question is, how tight does it cluster around that true mean? So if we've got this standard deviation or variance sigma squared here, what does this mean, this sample mean, 1 over n times that, how tight does that cluster around the one that we've got here? And we can calculate that. I'm not going to go through the details of this here. You can go through it in the Webb and Copsey book, but basically the variance, which is xi, the sample mean is the one that we've calculated. Xi is the sample. That difference squared is the variance that we measure, and the expected value of that variance turns out to be not quite an unbiased estimator for the sigma squared. So if we wanted to use that to estimate just this average of the squared values, if we wanted to use that to estimate what the variance was, we'd be slightly off. Now, fortunately, if n is very large, then n minus 1 over n is approximately equal to 1, and so it's pretty close. So in many cases, and actually for the assignment, we'll just use 1 over n. So we'll just use this estimator without making any adjustments. But if you've got a small number of data points, you might have to make an adjustment for that. But you can see because of that, sometimes instead of using 1 over n in here, you'll see in formula booklets that using 1 over n minus 1 is sometimes preferred as a better estimator for this one. Essentially, what's happening here is that the spread of where the mean is always slightly closer to the mean of the sample points than it really was to start with. So there's a slight adjustment there. Don't worry if you don't get this one, but just be aware that that's the case. So this one is sometimes preferred. So on the whole, though, if we want to estimate this, it's a pretty good guess just to take the sum of those, the average of those, and the averages of those squares, and that will give us our a rough guide to our mean and variance. So an interesting thing for us to do next is, well, we've already seen that the expected value of the sort of average that we want is this mu here, but for this thing that we measured as our mean, it's interesting to find out what the variance of that mean is. So we know that if we choose a single sample, the variance of that single sample is given by sigma squared, or the standard deviation is sigma. That's how we define our underlying distribution. But what's the variation of the sample mean? What's the variation of, if we take 20 points, average them, and give a sample mean, what's the variance of that? What we hope is that the variance is going to be smaller. We hope that on average it's going to cluster quite tightly around our mu, and that means that it will give us a good estimator for that. And if we calculate that, again, the details are in the Webb and Copsey book, the variance of that, the variance of something is the sum of the variances with 1 over n in here. So what we find is that actually the variance of this sample mean is the original sigma squared divided by n. So sure enough, the larger n you measure, the more data points you get, we end up with an estimate which instead of being this variance, we end up with a much tighter estimate around the same mean. So this is very good in terms of what we want to do. If you want to think it in terms of standard deviation instead, standard deviation is measured in the same units as that. The standard deviation is the square root of this, and so the standard deviation is sigma divided by root n. So actually what it means is if you've got 100 samples, the standard deviation of this is 1/10 as wide as it was to start with. And that will give you a rough idea of how accurately you want to measure that mean. But what this tells us is that the mean is never quite necessarily exactly where we want it. It's always going to be slightly different. And one of the things that you'll get to explore in the assignment is, suppose that this mean was a bit big, or suppose the mean was a bit small. How would that affect the decision that you made? You wouldn't anymore build a Bayesian optimal classifier. Your decision boundary will be in a slightly wrong place. How bad is that? And the assignment will give you a chance to go through and see what change that would make. So let's put all this together into actually designing our parametric Gaussian classifier. We need a covariance matrix. and we need a mean to put into our classifier. So the mean we just simply estimate as the mean of all the data points that come from that class. And that's the one that we use. The covariance matrix we'll use, supposing n is big enough for each class, we'll use this 1 over n times this outer product between these two. Each of these outer products will form a rank 1 matrix. We take the average of all of those, and that gives us our covariance matrix. So we use a little hat to say it's an estimate. So wherever you see a hat on something, it normally means an estimated value. So here, mu I hat is the estimated mean, and sigma I hat is the estimated covariance matrix. So again, be very aware of the different uses of the word mean. So we've got the true mean, which is the underlying distribution that we've got here. We've got the sample mean, which is the thing that we've calculated here. We're using the sample mean to be the mean of the distribution that we're going to assume is our model. And this sample mean itself follows a random distribution, and it will also have a mean and variance. So we've got about 3 or 4 different means that we're dealing with here. So just make sure that you're aware by going through this carefully of what these different means do. Finally, we also need, because the Bayes algorithm here, we need these prior probabilities. And we can estimate these just by counting the number of items that are in that class compared to the total number of things that are in all of the classes. So those are then the numbers that we can plug into our Bayes formula with this class conditional density, but with these sigmas and mu's as the estimated values instead of the true values. So that's the best that we can do for now. So then that leads on to what's the error from our decision making, and how bad is that going to be based on what we're then going to measure. So we've got some actual error that we're going to make here. So this is the sum over all classes. We divide our pattern classifier, divides into regions SI hat, and I'm using the hat here because this is our classifiers that we built using the estimated values. And essentially this is saying that the error here is it's weighted by the probability of that class, but anytime you're doing the wrong class, then it's weighted 1. If it's the correct class, so it's actually omega I that you do your assignment, then it's weighted 0. So we're subtracting those two. We had a similar formula to that last time. So that's the true error that we're going to have. But in order to calculate that, we need this prior probability, but we also need to know this true probability distribution. So in reality, we can't measure this actual error. We can't know how well our classifier is doing. So instead, we can measure, well, the true probabilities here come up just because we do that based on the samples that come out. So that will actually happen according to what we measure. But here, this is our distribution that we've measured from the choices that we make. This is the design set distribution that we're able to model, and we've estimated that, so we can use that. And this is the so-called design set or training set error. So we can estimate that. And this gives us a value that says, suppose we use these samples to train our classifier, how well will it do to train if we tested it on those same samples? So in a way, that's sort of cheating. It's saying, here's some things, design your classifier to classify these things. Now, how well does it do on the same things? Actually, that's easy because you've designed your classifier to do it. It might not be perfect, because you might still have some overlaps, but this tends to be better than it should be. So in practice, we need to hold back some other data points and have this probability density that we estimate from a test set distribution. And theoretically, this will give us a better estimate of how it would do on some unseen samples. Yeah. So those are the regions, those are the regions defined by the boundary, the decision rule that you've built. So we talked last time about building a decision rule based on knowing what the real distributions were. Here, we only have estimated distributions, and we have to build the boundary based on those estimated distributions instead. Yes, in theory. Now, in practice, we won't do this. We'll do something simpler. But that would give us the real estimate of the errors. But just to give you an idea of, so this is the actual error. So this would be the design error. This is the training set error, and this is the test set error. So again, there are lots of errors to keep track of. Initially, we've got the theoretically best error. That was what we called the Bayes error last week. We've got the actual error that you get, you design your classifier, it's not quite in the right place, so this error is going to be slightly worse. The design set error, this is actually going to underestimate this one, probably. It's going to give you a more sort of rose-tinted glasses, if you like, view of your data. It says, oh, look, we're fine, we can classify all of our training set, everything's lovely. But actually what you haven't taken into account is there are some things you haven't seen, and your classifier is not so good at those. And the test set is much better at those. And so in practice, what you find is that your test set is normally larger than the design set. It's normally larger than the Bayes error, but actually, because it's a random process, you may have got lucky with your training set. They may be really easy to classify. Sometimes you may have been really unlucky with the training set. They may be really hard to classify. But in general, the larger training set, test set that you've got, the better the estimate is. But this thing is always true. The actual error is never better than the Bayes error. And so again, in the assignment you'll be doing, you can see this. You'll calculate the Bayes error, and then you'll calculate the actual error, and you'll see that those are not as good. So let's have a look at trying to do some of this in a bit more practice for a sort of practical example. Let's look at how this would work for a one-dimensional Gaussian. So we're going to stick in one dimension and see how this works. And so actually the key thing that we're working with here, let's choose another color here, is that let's suppose we've got two classes. We have to choose a boundary point, but the error comes up because some of the things on that side are going to be assigned into the wrong class. So what that means is that we need to know how to estimate the area under the tail of a Gaussian. And so this is the thing that we want to know, this integral from k to infinity of a normal distribution. And this is a nasty thing to do. You can have a go if you like, but actually I wouldn't recommend it, because you can either do it using a table or you can do it using a graph. Here's a table that's in the data book. So there's a EEE formula booklet, and you'll find a copy of that on Surrey Learn, and on pretty much the last page, you've got the error under a Gaussian error curve. You can also do it using a graph. There's a way of doing it by reading off things across here. We can look at an example later. But this is the thing that we want to measure. It's the error under this. And in order to do that, we need to standardize our distribution. So normally our normal distribution has this x minus mu over sigma square, all squared at the top. And we will need to normalize that so that we use a value k, which is just equal to x minus mu over sigma. Once we've done that, then we can do the calculation on this graph. Or if you've got MATLAB handy, you can ask it for the Q function or the error function. You have to be a little careful which one you're using, because some might be different to others by a factor of a half. So some do the integral from there up to infinity, some do the integral from the mean up to the point. So they're slightly different, but they do essentially the same job. You just need to remember which one it is that you use. So this Q function is the one that we'll be using. The table in the formula booklet gives the area between the center and the point. So it gives this area instead here. So just be careful when you're using those that you know exactly which area it's going to be calculated on. It's not an easy calculation to do. Depending on the calculator you've got, you may or may not have it on your calculator. So that's why if you did need it in an exam, then there'll be these tables available for you. So this is the key thing that you'll be looking to do, and in the assignment you'll get some practice at doing that by measuring the Gaussian tails through there. So I'll give a little bit of overview of the assignment in a moment, but just to finish off this section, actually there's a practical way. So here we measured what we thought is the theoretical error, but the practical error that you do is just to count the number of mistakes that you make. So you have a large enough test set, you see what percentage is correct or wrong. And so this is very straightforward. Your input value goes in here for your test set. You apply your classifier and you get the estimated class from that. And then you just compare that to the known value from your test set pattern. And that comparator gives you an error value. Now in the simplest case, the error value is 0 if it's the same, or 1 if it's different. But if you remember back from last week, we talked about different types of errors that you can make. You might want to have errors that are weighted differently, so you can include that in your comparator. You then just average the number, and that gives you an error estimate. So this is a very simple way of doing it, but you do need to be aware of the limitations. If you've only got 20 data points, then actually your error estimate is only going to be accurate to steps of 5%, because you're either going to get 0 error, 1 out of 20, 2 out of 20, all the way up to 20 out of 20. So it's going to give you 0, 5, 10, 15% error. So sometimes I've read even research papers from sane researchers where they say, oh, my accuracy is 12 point something, and I've got, or my error is 12 point something, and that's much less than somebody else's. But actually, the accuracy with which you've measured that error, if your training set only had 100 data points in it, then you've only got 1% resolution in your error. And because of what we saw here about the number of the variance in the estimate, just being the variance being 1 over n of the number of data points, or the standard deviation being 1 over square root of data point, if you had a very random distribution of errors here, then your error estimate could be could have a wide variance as well. So you need to be very careful about claiming that some machine is better than another machine because you've got 95.7 and the other person's only got 95.6 in terms of correctness. So these are things that if you remember back to your statistics about statistical significance, this is the sort of thing that you really ought to be doing, statistical significance testing. You want to, I'm not going to cover it in this lecture or this course, but you can, if you go from the point of saying, we want the hypothesis that these two classifiers are the same, and we want to discount that hypothesis. We want that's our null hypothesis. We want enough evidence to say, no, they're not the same. and that would be a way of saying one is statistically significantly different to the other. But we're not going to go into that for the moment. What we are just going to mention about the this error estimate, so that's how we do that. This bias and variance will come up. So depending on the shape of the distribution that we get, because it's calculated by a tail of something, it may not have a nice, easy Gaussian distribution, but these properties that we get that come out of it means that actually we can look at the expected value of this error estimate and think, okay, it may not always give us the exact value, it will vary around a bit. What if we did it many, many times and took the average? Actually, we can calculate that the expected value of that would be the underlying error that we measured. So for the actual decision that we made, it will actually average up to give us our true error. So we'll never see this, but what this tells us is that it's an unbiased estimate. So if we were to do it many, many, many times, then the underlying distribution that follows has a mean in the right place. So there isn't, so the error estimator at least does something sensible. But it has a variance, and we can estimate the variance as well. That turns out to be, if the error is E, then the variance is going to be E into 1 minus E. So this value means that for very small values, the variance is roughly around E. For values around a half, this is going to be around a half squared. So we could have quite a large variance if our error is roughly 50%. So you have to be very wary about large errors in this case. So what this does tell us is that the expected value of this error estimator is in a sensible place, and it's an unbiased estimator. So in other words, its average is in the right place and has a particular variance here. And the variance of this error estimator decreases as the number of samples increase. So the variance, we're not going to calculate this one, but as you have more and more samples, you'll have a tighter and tighter distribution. And this is good. This says bigger a test set, the closer this is to actually being reality. So this is the variance for one estimator. If we did it with many samples, that would work. So this is one error estimator that we can use, but actually there are many different performance measures that you will see that people will quote in pattern recognition type problems. So in a two-class case, there's a classic way of dividing the predicted class and the true class from each other. The phrase false positives is often used informally, but this is really where it comes from in terms of a formal sense. So if your true class is a positive one, and the predicted class from your classifier says it thinks it's a positive one, then that's a right answer, and it's a right answer for a positive class, so this is a true positive. But if the true class was negative, but your classifier thinks it's a positive answer, this is a false positive. So the classifier thinks it's a positive, but it actually isn't. And so this is the sort of thing that, so for example, the case a couple of weeks ago was discussion about face recognition for criminals on the run or something. You have something that says, oh, look, this might be one of the people that you're looking for. But there are really so few of them that you might end up classifying an ordinary person as one of these potential suspects. That would be a false positive, because in the true case, it's not the person that you're looking for, but the classifier thinks it is. And when you've got very unbalanced data sets where the number of positive examples is very small, you would expect to have a significant number of false positives, and you need to design your process to allow for that. On the other side, there may be true classes that your classifier thinks are negative. This is a false negative, and that can be a problem for you. You might miss things that you should pick up. If you've got a diagnosis system that misses a particular disease, that will be a false negative, and so you don't catch that disease. The alternative at the far end is if the real class is negative and the classifier thinks it's negative, then that's a so-called true negative. So the idea here is the true, and true means that the classifier has made the correct decision, and false means the classifier has made the wrong decision. Then just the confusing bit to remember is which is positive and which is negative. And if you can remember, it's the predictive class that says positive. True positive. A false positive is when the classifier thinks it's positive but it isn't. So you could think of it as a false positive indication. So the classifier thinks it's positive. It's very easy to get these two swapped when you think of this graph. So just this table. So just remember that one. So there are various sort of measures that are calculated from these. The false positive rate is the number of false positives divided by the total number of things that happen. There are things like precision and recall. So imagine that you're building a search engine. You want people to be able to type in, find me examples of butterfly pictures. Precision says, out of, let's say, 10 examples, how many of those are actually butterfly pictures of the ones you asked for? So suppose you want 10, you're given what the classifier thinks are 10 positives, how many of those really are positives? That's precision. Recall says, I want all of the butterfly pictures that you've got. And recall says, out of all of the things that you should have found, how many did you actually find? Or did you miss any? So that might be things where you're sure you put that letter somewhere, you found all your other letters, but that letter to the bank that you wrote a long time ago, you can't find it. That's a recall failure. You haven't found that particular thing that you knew you wanted. So there are various measures in here that you can use, and those are things that you'll see discussed in many papers from there.
The definitions there seem to be normalising by the number of negatives and the number of positives, but not the total.
Yes, that's right. So this particular one on accuracy, this one does, so P and N is the number of positive and negative examples. And so in this case, total accuracy, you take all of the examples and say, what are the true positives and true negatives divided by the total number of things that you've got? So that's, but the other ones, yes. That's right. So the false positive rate says out of all the things that should be negative, how many actually come up as false negatives? And so that tells you, that gives you a better idea, particularly for an unbiased data set. Okay, so that's really where I wanted to get to from here, except just to say a few words about, to introduce a little bit more about the assignment, to give you some general guidance on the assignment that's set. So this was made available last week, and you might have started already on the first part of this, but the later parts really required the information from this lecture to be able to do them. But there is, in addition to this, there is a comprehensive help sheet that will help you to work through this example. So if I can just find the help, the worksheet that I've got from here. Put that. Okay, well, while I'm doing that, you also have this table of numbers that tell you your personal numbers to use for the assignment. If you don't find your number, maybe you moved on to this course late, then let me know and I'll generate some other numbers for you as well. But just to give you an overview of the assignment and how it works, this is really to explore all of the concepts that we've been talking about from last week and today, using two-dimensional classes with equal covariance matrix. So we've got equal covariance matrix. So what does that tell us about the decision boundary? It's linear. Yeah. So this is a linear classifier, and the dimensionality is 2, and because of that, actually what we will find in this case is that when you build the two-dimensional classifier, the distance between the densities is actually in the same direction as the eigenvalues and eigenvectors rather of the covariance matrix. What that means, in other words, is as a picture, you have two covariance matrices that might be like this. The shape will vary for you, but if you draw a line along there, you can actually find the decision boundary at that point, and really you only need to look in that direction. And so really what this turns into is a one-dimensional classification problem. So the first part of this is actually about working out where the classes are in your case, sketch the equal probability density ellipses. So I just did them here by hand, but you need to do that for your own. Then you can work out where the classification boundary is. Then we can work out what's the Bayes optimal decision rule. That's the thing that we did at the end of last lecture, just at the beginning of this one. And we're going to assume that the prior probabilities are a half. That's corrected in the one I've got. That should be P of omega 1 is P of omega 2 as a half. So that also simplifies the problem. So we've got equal probability and equal prior probabilities. We've then got that's part 2. This part is saying, what's the theoretical best error that we could get? Somebody actually told us in reality what the classes really were. Let's calculate how good those will be. Now, question 3, this is to move on to, what if we didn't have that, but we were training them using a training set instead? Now, this is a paper exercise, so we're not going to need to use a computer for this one. But what it says is that if I'll just zoom in a little bit, because I know this is a bit small, I'm not expecting you to read it on the screen, but what we're saying is, suppose that one of these classes, one of them the estimator was dead on, but the other one was slightly wrong. And in this particular case, it's saying, suppose that it's slightly wrong by 1 standard deviation of that sample mean. Remember, the sample mean has got this tighter distribution, but it does vary. It would be very easy to be 1 standard distribution away. About a third of a normal distribution is more than 1 standard deviation away. And so we're going to assume that this is slightly wrong. How much worse does that make the result? And that's really the point of part 3. So calculate the new decision boundary, work out what bits of the tail are chopped off, what the areas under the tail are, work out how bad that is now. So what that bit says is, suppose you've got a training set, how much worse does that make that? And then the last part, question 4, is, well, we don't actually know how to measure that, so we're going to have to use a test set. The test set itself has some variance. Suppose it's a bit big or a bit small, what values would that come up with? So you'll find out how much those differ from the things that we estimated from before. So that's really the assignment. So you've now got everything that you need to do all of the assignment from that. If there are any things next week, I can help out on that. Otherwise, I will see you next week. And tutorial 3 is up and will be done first thing next week. Okay, bye for now.